So those are the broad techniques. So let me move on and talk briefly about applications and areas for further work. So there are really two sort of key applications of these methods. One of the original motivations for developing these things was the limitations of simple indices derived from the diffusion tensor as markers of white matter integrity. So things like fractional anisotropy, mean diffusivity have become popular for use in that way. But obviously they're limited because they're also affected significantly by the configuration of fibres. So one of the hopes for these techniques was, if we can characterize the distribution of fibre orientations more precisely, then we might be able to sort of factor that out and derive more robust markers of white matter integrity. And some people have suggested markers that derive from these techniques, but really these things haven't taken off in a big way, and I think there are opportunities there to exploit. The other obvious application is tractography. So clearly these things give us more information about the distribution of fibres in each voxel than we get from basic DTI, but actually we have to work quite hard to exploit that extra information to improve tractography. So just simple deterministic or streamline tractography, the obvious thing to do is use the peaks of these functions as fibre orientation of estimates of fibres to tell us which step to make at the next iteration. But there are subtleties in making decisions about which one of these fibres to follow. For probabilistic tractography, the challenge is even greater. We also have to model the uncertainty in these fibre orientation estimates, and that can be challenging. Although there are various ways of approaching that in the literature. So moving on to sort of current and future challenges, the techniques that we've seen are actually pretty good at resolving fibre orientations and telling us, what the directions of different populations of fibres are. But there are other configurations which remain problematic even for these more sophisticated techniques. If we go back to my old slide from the beginning showing these different configurations, one thing I glossed over neatly was the fact that these fanning and bending configurations actually produce identical scatter patterns. And since this is the sort of fundamental object that we measure in diffusion MRI, because they produce identical scatter patterns, this means that in isolation we can't distinguish these kinds of configuration, even though visually they're obviously very different. The clue to why these things are indistinguishable we can get by looking at these fibre ODFs. Of course, both the fibre ODF and the scatter pattern take some contributions from all over these voxels, and in combination, the distribution of fibre orientations in both of these configurations are the same, and so that's what leads these scatter patterns to be the same. So is there anything we can do to resolve these different, the ambiguity between these configurations? And there are other configurations which are ambiguous in similar ways. Well, the clue is in the fact that I said in isolation they're indistinguishable, and the angle that we have on potentially distinguishing these kinds of configuration is by looking looking at the surrounding image. Because fibres in the brain are continuous, there are only certain configurations which can naturally fit together. So, for example, if we're in the middle of a large fanning structure, we're unlikely to see suddenly just a bending structure in the middle of a whole load of fanning structures. So that's the angle that we can potentially use the neighbourhood of the image to resolve these ambiguities. So let's look quickly at what people have done so far. So early work looking at sort of fanning and bending, Kieran Sunarine hypothesised that the shape of the peak of these fibre or diffusion ODF functions might reflect the degree of fanning and bending. So the idea was that if we have these kind of planar configurations, the shapes of these peaks will reflect that. And he showed nicely a demonstration of this. So these figures are showing the sharpness of the peak on the left, so we get sharper peaks in dense white matter, but then the peak anisotropy on the right. He shows nicely that this peak anisotropy is high in regions of known fanning, and in fact the orientation of the anisotropy of those peaks also reflects the known orientation of the fanning. A couple of examples from this year's ISMRM program, people starting to develop models of fanning and bending that enable us to quantify the amounts of fanning and bending. But again, these things are all in isolation, so we still don't help us distinguish these kinds of configuration. Some nice work from last year by Peter Sabadiev kind of sets a precedent for using the surrounding image structure to resolve these kinds of ambiguity. One other ambiguity, something again that Donald touched on, between this kind of low-level interdigitating crossing and more sort of partial volume of fibre bundles running close to each other. So Sharon Najati-Galani again last year used a super resolution technique to try and resolve this kind of ambiguity. So the idea was to use a kind of multiple stick and ball model, a bit like Behrens' model, but to include some spatial separation of the different stick compartments by using the image neighborhood. And he showed nicely that he could detect the boundary between these two fibers, the cingulum and the corpus callosum, which are run orthogonally but very close to each other. So he could locate the boundary between these two fibers to subvoxel accuracy using this technique. So there's a zoom in to show that he detects the boundary to this subvoxel level. Okay, so that's about all I'm going to say. Let me just finish by plugging two forthcoming books, one by our esteemed host here, another by Tim Behrens and Heidi Johansen-Berg. So there are chapters in both of those books which go into a bit more detail of on what I've been saying in this talk, which you can look up if you feel the need, and that's it. Special thanks to Kieran Soonarain, who was my co-author on those book chapters and produced some of those nice graphics for the fibre configurations that I've shown. Thank you.